Here we will examine structure and properties of simple organic molecules, and those are alkyl halides, alcohols, ethers, and amines. Now we are going to look at properties of alkyl halides. Alkyl halides contain carbon-halogen bond. Carbon utilizes its hybrid orbital. If it's saturated compound, that means sp3 hybrid orbital, and halogen utilizes its p orbital for bonding. Which p orbital depends on the halogen atom. Each halogen atom will use its valence p orbital, and in each case it's going to be different p orbital. So in case of fluorine, that's 2p orbital. That's lowest energy, simplest p orbital. That p orbital has two lobes, one above, one below the plane of the nucleus, and it has a planar node that goes through the nucleus. That planar node is shown here as dashed line. So this orbital is actually relatively small in size, and it's a very good match in terms of size with carbon hybrid sp3 orbital. Next one would be chlorine valence p orbital, and that's 3p orbital. That one is a little bit different from fluorine's orbital. We can see that in addition to planar node, it also has a spherical node. In this case, spherical node appears to be an ellipse. The reason for it is, as you may recall, that these are stylized representations of p orbitals. Stylized representations represent them a bit elongated to show direction of the bonding. But as we elongate them to show direction of the bonding, then what would be spherical node looks like an ellipse. This spherical node bisects each of the lobes, upper and lower, into two lobes. And as it bisects them into further two lobes, then there is a change in the sign of a wave function. Again, signs of the wave function are shown as colored and white. And so only orbitals that have same sign of wave function can overlap to form a bond, which obviously means that not the entire lobe, upper or lower, can overlap with carbon hybrid orbital, because some of them will be of wrong sign. Then we have 4p orbital of bromine, which is valence orbital of bromine. So that one has two spherical nodes. Again, they are shown as ellipses because this is stylized representation. And of course, that means that we have what we can say more slices, more parts of the orbital where wave function keeps on changing from plus to minus and plus to minus, or colored to white and back to colored. And again, that results in somewhat inferior overlap with hybrid orbital of carbon, because as wave function changes, only parts of the wave function that have same sign as carbon wave function can overlap. Those that are out of phase, that have opposite sign, cannot overlap. That will result in destructive overlap. Also, you will note, to some extent with chlorine, but definitely with bromine, already there is very large orbital. That will result, as you will see next, in considerable orbital size mismatch, which will result in weaker bond. And finally, iodine 5p orbital is its valence orbital, and you can see first it's rather large. What probably would strike you right away is how large that orbital is, but also in addition to typical planar node of a p orbital, this one has 3 spherical nodes. So that further keeps on slicing this p orbital into more and more individual slices. Obviously, that's going to likely result in much longer and much weaker bond. Here is how bond is formed on example of simplest and, as you will see in a minute, strongest bond, carbon-fluorine bond. So it's sp3 orbital of carbon, shown in black on the left. We are showing only the bonding lobe of sp3 orbital of carbon. So it's sp3 orbital of carbon that overlaps with 2p orbital of fluorine. It will overlap with yellow part. We assume that those two, with yellow lobe, that those two are in phase, have same sign of wave function. So the two of them overlap to make molecular sigma orbital, and that sigma orbital is carbon-fluorine bond. So here are corresponding bonds that are formed in each case between each halogen and carbon. So carbon-fluorine bond, what you can see here is that there is actually a pretty good match in terms of size of orbitals, and also there is very good match in terms of phase of the orbitals. So we have very good overlap. We would expect strong and short bond. In case of carbon-chlorine bond, we can see first that there is a little bit of mismatch in terms of size. Chlorine p orbital is a bit larger in size, and so overlap is not as good. And also, of course, we can see that large part of the lobe that should overlap with carbon sp3 orbital cannot overlap because it is out of phase. It's shown in white. And then when we get to carbon-bromine bond, we can see that mismatch in size is even greater. That means overlap becomes progressively inferior. It's not as good as in case of carbon-chlorine and certainly not as good as carbon-fluorine. So we can see that there is very large mismatch in size and between carbon bonding orbital and bromine bonding orbital, and also, of course, again, not the entire lobe can overlap with carbon orbital because part of it is one slice is out of phase. And finally, carbon iodine. Now we can see rather large mismatch between p orbital of iodine and sp3 orbital of carbon. We would expect very poor overlap and as a result very weak bond, and of course because of the numerous changes in wave function in that particular lobe that should overlap with sp3 hybrid orbital of carbon, we would expect even further weaker overlap. So carbon iodine we would expect very weak bond, and of course very long bond, both because it's weak and because iodine p orbital is so large. So qualitatively, when we examine these four bonds, you would expect carbon-fluorine to be strongest and shortest, and then carbon-chlorine a bit weaker and longer, carbon-bromine noticeably weaker and longer compared to carbon-chlorine, and carbon-iodine the weakest and the longest bond. Here in this table we have quantitative data for length and strength of alkyl halide bonds. So when we consider carbon-fluorine bond, on the left we have ball and stick model. By the way, fluorine here is shown as kind of yellow-green. Typically it should be yellow. By convention we represent fluorine as yellow, but this particular program that I used apparently for some reason shows fluorine atom as kind of yellow-green. So carbon-fluorine bond has bond length of 1.39 angstroms and bond strength of 115 kilocalories per mole. That's actually rather short and rather strong bond. Compared to generally bonds in chemistry, that is short and strong bond. And in a reaction, we would not expect these bonds to break easily. So we actually would not expect fluorine to be a leaving group. And here is the same molecule. This is fluoromethane, shown as space filling model. So you can see relative size of fluorine to carbon atom. They are very similar in size. Fluorine may be just slightly smaller than carbon. And then carbon-chlorine bond. When you look at the model on the left, and chlorine is shown as it should in green, when you see model at the left, you can see that bond is noticeably longer compared to carbon-fluorine bond. And that's shown in actually measured bond length of 1.78 angstroms, and of course noticeably weaker bond compared to carbon-fluorine bond. So its strength is only 84 kilocalories per mole. That's actually bond that can be broken in the course of a chemical reaction, organic reaction. So we would expect carbon-chlorine bonds to be frequently broken in the course of an organic reaction. And here is space filling model, and now you can see that chlorine is actually much larger atom than fluorine and actually larger than carbon. Next is carbon-bromine bond. You can see that this one is even larger compared to carbon-chlorine, and you can see that bond length is 1.93 angstroms and bond strength 72 kilocalories per mole. That's actually rather long and rather weak bond. If this bond is present in a reaction, you would expect that very frequently that bond will be broken. In fact, more likely than not, if there is a reaction, this bond will be broken. And now we have here a space filling model, and you can see that bromine is even larger than chlorine. And then we have carbon-iodine bond, even longer bond than carbon-bromine. So its length is 2.4 angstroms and strength 58 kilocalories per mole. That's actually a very long and very weak bond. You would say extremely long and extremely weak bond. In fact, this bond is so weak that carbon-iodine compounds, iodoalkanes, have to be stored at low temperature in the dark. So we keep them in brown bottles, typically in the fridge, because if exposed to ordinary light, like green light actually, this bond would break. So ordinary visible light has sufficient energy to break these bonds. So if we were to leave alkyl halide just lying around in a beaker, in an open beaker, or in a clear bottle, it's likely that it would decompose because carbon-iodine bond would be broken by the visible light. That indicates how weak this bond is. And here we have space filling model, and now you can see how large iodine atom is and how much larger it is than carbon. Of course, in each of these cases, we are only considering bond length and bond strength. In case of alkyl halides, we don't consider any molecular geometry because halogen forms only one bond and there is no geometry on the halogen. Of course, carbon atom does have geometry, but we have considered geometry of carbon atoms earlier. Geometry of molecule around carbon atoms or substituents on the carbon atom earlier. So no geometry here, we are only considering bond length and bond strength as part of properties of alkyl halides. Alcohols and ethers can be considered to be formally derivatives of water. So we have water molecule shown in the upper left, and an alcohol can be formally generated by replacing one of the hydrogens of water with a hydrocarbon substituent, and ether replacing both hydrogens of water with two hydrocarbon substituents. We have seen earlier in this course that molecule of water has tetrahedral shape of the electron cloud. At the electron cloud, that means bonds and free electrons. And of course, shape of the molecule, then we are only considering positions of atoms, we don't consider free electron pairs. So shape of the molecule is bent. So molecule of water has tetrahedral shape of the electron cloud and bent shape of the molecule. That means that alcohols and ethers have the same properties. So both alcohols and ethers have tetrahedral shape of the electron cloud, substituents on the oxygen and free electron pairs, two free electron pairs, and bent shape of the molecule. So both alcohols and ethers are bent. The only difference between water on one hand and alcohols and ethers on the other is that in case of water, we know that bond angle hydrogen, oxygen, hydrogen is 104.5 degrees. In case of alcohols and ethers, that angle varies a little bit, and it depends on the size of substituent or substituents are. The last class of compounds that we are going to examine are amines. Amines can be considered to be formally derivatives of ammonia, so NH3, where one or more of the hydrogens of ammonia are replaced by hydrocarbon substituents. And so, just like ammonia, amines have tetrahedral shape of the electron cloud. That means substituents and free electron pair on nitrogen. There is only one free electron pair on nitrogen. And they have trigonal planar geometry. Here we have in the top row shown general formulas of, from the left to right, primary, secondary, and tertiary amine. And in the second row, we have the actual examples with methyl substituents. So methylamine as primary amine, dimethylamine as an example of secondary amine, and trimethylamine as an example of tertiary amine. Finally, in the bottom row, there are ball and stick models of each of those. So geometry is the same as that of ammonia. Now in ammonia, bond angles are 107.3 approximately. That would be hydrogen-nitrogen hydrogen bond angles. In case of amines, bond angles vary a little bit, as in case of alcohols and ethers, and the actual bond angles depend on the nature and size of substituent R. This completes our brief review of properties of simple organic molecules. Next, we are going to look at intermolecular interactions.